In this video, we're going to take a look at periodic trends, looking at the properties of atomic size, ionization energy, and electronegativity. So first, take a look at atomic size. And trying to figure out the size of an atom is really difficult because of how small they are and because you can't really see these atoms, and the outermost parts of these atoms are the electrons as they are moving around. So the way in which we can measure the atomic size of an atom is take two atoms of the same element that are next to each other and using that small dense nucleus and taking a measurement between two nuclei of these two adjacent atoms of the same element, cutting that in half, and that will give you the radius of one atom. So the general rule is as you move from top to bottom down a group, the atoms get larger, and as you move left to right across a period, the atoms get smaller. So let's take a look at the group trend first. As you work down a group, why does the atom get larger? Well, we have two different things that happen as you move down a group. You have more protons and more neutrons, but in particular the protons being put into the center, into the nucleus, but you also have more electrons being filled into more energy levels. So these kind of are opposite of each other. One wants to make it get larger, one wants to make it get smaller, so which one wins out? Well, it's the amount of shielding that happens from the inner electrons to those outermost electrons that blocks the pull of all those protons in the center, preventing it to suck in like a magnet, making that atom smaller, so the atoms get larger as you work down a group, again because of the shielding of those inner electrons on the outermost electrons, preventing the pull of the protons in the center. However, as you work across a period, you're usually filling into the same energy levels. You're not gaining any shielding as you work your way across. Only the atomic number, the number of protons in the center, is changing, so it causes the atoms to get smaller as you work left to right, because now I have a greater pull on the electrons from the center, but the same amount of shielding from the inner electrons to the outer electrons, so therefore the atoms shrink and get a little bit smaller because of the greater pull from the center protons. So here we'll see what that kind of looks like as you work your way down a group and across a period. So let's look at period 3 there, sodium to argon. So sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. As you work your way, again, left to right across the periodic table, we see that there is a downward trend from sodium all the way across to argon. So across that period, again, we see the atomic size go down. And then let's look at the yellow ones up top, the alkali metals, lithium, sodium, potassium, rubidium, cesium. We see the trend of it getting larger as you work down group 1A. So ions, when an atom gives up or takes on an electron, giving it either a positive or negative charge, is also going to change the size of these atoms. So positive and negative ions are formed, again, when these electrons either transfer from one atom to another. And we know metals like to give up electrons and nonmetals like to take on electrons. And those metals, when they give up their electron, they make a positive ion, or what we call a cation. Once it loses one or more electrons, and you have an unbalance between the protons and the electrons for a given atom. And then conversely, when you take on electrons, you become negatively charged and you are an anion. So metals, again, usually like to give up their few valence electrons, making positive cations. Nonmetals, which have almost full valence shells, like to take on to complete them. So from that, we're going to take a look at ionization energy. Ionization energy is the amount of energy that is required to remove an electron from an atom. So the more difficult it is to take an electron, the greater the amount of energy needed to do that. So those that really want to take on electrons, it's going to be really tough to get an electron from them. And those that are pretty willing to give them up, then they're not going to put up much fight and they'll have very little energy required to do so. So the first ionization energy, the amount of energy it takes to remove the first electron, within a group, it decreases, and within a period, it increases. So let's take a look at why. Within a group, why is the amount of energy decreasing? Well, again, it has to do with that shielding. As you have more electrons shielding the pull of those inner protons, there's not as much pull from the center on those outermost electrons, those valence electrons, making it a lot easier to remove one. Since that there isn't as great a pull, they put up less of a fight, making it, again, much easier to remove one from it. And then as we work across a period, why does it become more difficult? Well, again, just like we talked about the atomic size, as you move left to right, we're not filling into greater energy levels, so therefore the amount of shielding remains constant. So I have more protons going to the center, getting a greater pull from the center of that atom, the protons on those negatively charged electrons, with the shielding remaining the same, therefore making it more difficult to remove those electrons because of that greater pull from the center. So taking a look at it, we see here, again, as we work our way down groups and across periods. So we'll go to that second period again, and we see sodium, and we work our way up magnesium, aluminum, all the way across to argon. We see it increasing in general. Now, not quite the same trend as we saw at the atomic size, not as nice a line, but we do see, again, a trend. It does increase left to right. And then same thing, as we work our way down group 1A, we do see there is a slight downwards trend. Same thing, working our way across down group 8A, from helium across to xenon, there is a downward trend. And this we should expect because we know that group 1A, again, is very willing to give up an electron. They have one valence electron which they want to lose, so they're not going to put up much fight. And then conversely, the noble gases, which have a nice full S and P sublevel in their outermost ring with those 8 valence electrons, are going to be really difficult to get an electron from because they're very stable. We see them at the top of each of these periods. So then looking at the ion size, we see that when a cation is formed and you lose electrons, you're emptying out that outermost level, so it's going to be smaller than the atom from which it came from. Conversely, anions taking on electrons, they're going to become larger than the atoms which they formed from because they're taking on more electrons, and there's a less ratio of electrons to protons, so therefore there isn't as great pull for each electron from the amount of protons, making it a little bit larger. And the last trend we're going to look at is electronegativity, an atom's ability to attract an electron when it's in a compound. So whether it's molecular and they're sharing the electron, or it's ionic and it's such a discrepancy between how badly they want that electron that one person actually takes it and the other person loses it, and you have an ionic compound because of that transfer of the electrons. But who is more able to attract that electron? So if you have a large electronegativity, you really badly want electrons, and if you have a low one, you don't really want them at all. So in general, we notice that working away from top to bottom down a group, we have a decrease in electronegativity, and left to right, as we work way across the periods, it increases. We see this for the same reason as we've kind of already discussed. Look at the number of protons in the center versus the amount of shielding. As you work your way down a group, again, there's more shielding, so those outermost electrons are going to have less pull from the center, so it's also therefore going to make it much more difficult to pull in an electron from somebody else. Conversely, again, at the top, where you have very little shielding, it makes it much easier to pull in electrons from other atoms that is bonded to. And then conversely, left to right, well, why is it increased left to right? Because again, there's a greater pull from the center, making it easier to pull in electrons. Plus, as we know, those valence electrons for the first couple groups is very few. They want to give them up to make a stable electron configuration. And then conversely, on the right side, where you have the nonmetals, they're so close to being like a noble gas, they really badly want to pull in 1, 2, or 3 electrons to complete that outermost ring. So we kind of put a big bow on it all and take a look at all the trends all together. Again, we see left to right versus top to bottom, and there's always an opposite as you work your way left to right and top to bottom. So if the atom gets larger top to bottom, then it's going to decrease left to right. Ionization energy decreases top to bottom, so it increases left to right. So if you can remember one, then the other one is just the opposite, and then it's just a matter of which one makes more sense. Well, for atomic size, again, if you're drawing out a Bohr diagram, you just know you're adding more and more rings, so definitely it's going to get larger as you go down, so it must get smaller left to right. For ionization energy, again, the amount of energy to remove an electron, well, we know metals really like to give up electrons, so they're not going to put up much fight. So left to right to the nonmetals, then it's going to be much more difficult to remove them. And we know those noble gases with a perfect electron configuration really badly don't want to give up electrons. They're going to be the most difficult ones to get electrons from, so you have the greatest amount of ionization energy. And then for electronegativity, we know that metals, again, don't want to take on electrons, so therefore they're not going to have a great electronegativity, where the metals on the right side do want to take on electrons, so they have a much higher electronegativity, so therefore top to bottom it must decrease if left to right it increases.